All right. Well, good evening, everybody, and welcome to a quick run over Sporadic E. The approach I'm taking is why. I'm not that bothered about actually working Sporadic E. Yes, I am. Of course I am. It's great fun. But that's not what tonight's about. Tonight is about asking the question, why does it work? What is it about? What's going on? Because if we can say what's going on, then perhaps we can do something about saying when it's going to happen. Now, there's an awful lot of myth about this. There's a lot of people, almost soothsaying who say, yeah, we're going to have a good day tomorrow. And as I'll illustrate, that's really not possible. So we'll see how that goes. And please do challenge these thoughts. I may say things and you may disagree, and that's just fine. In which case I'll be saying to you, well, okay, tell me. So there's no shortage of speculation about why Sporadic E works. And we're probably almost at a point where we know why it does work. The difficulty is that it doesn't help us actually predict it. It doesn't help us say tomorrow's going to be a good day. Or we've had a great day today, therefore tomorrow's going to be a good day. So we're looking for predictability and trying to be the same way as we can, for example, with aurora, where we know when the sun spurts out some plasma, we know when the plasma hits, splats around the top of the Earth, and we know that if there's enough energy in it, then it'll set up these spinning columns, and those spinning columns will may turn out into an aurora. But we're starting to get quite accurate at it. If the indices are right, then we've got a good chance of saying, 50-50 chance, yes, it's going to be a good day tomorrow, not tomorrow, but as it happens towards the hours beforehand. The difficulty with Sporadic E is, of course, we're trying to say, well, is it going to happen in the next few hours? And of course, the answer is, well, at the moment, we seem to only be able to say it is happening. We've have difficulty in actually predicting. So anyway, we'll away about Sporadic E. Where I came into this in 1984, thereabouts. And I did not come into it as an amateur. At that point, I had a ham license. I got a ham license when I was 17 or so. And I'd gone off to work in telecoms, and I was involved with, at that time, with Philips in consulting, in the propagation consulting group, and we were asked for a view. Is the 47 to 68 meg region, in other words, the old band 1 television, is that going to be a viable land mobile band? And Ofcom were at that point intent on selling it. They wanted to know whether or not it could be sold, whether it had value. And of course, something only has value if you can use it, you can do something with it. If you can't use it, then clearly it doesn't have any value. And of course, the Band 1 TV was all coordinated. It was super coordinated. You had a station in Prague, and the station in Prague would be coordinated with the station in the Midlands of the UK. And all of that coordination meant that there was no interference. Now, as soon as one nation starts to do one thing with a band, or does things on a kind of unlicensed or ad hoc licensing, if you like, base station by base station licensing, you don't then want to be coordinating base station by base station. It's one thing to be coordinating high power transmitter with high power transmitter. It's a different thing to actually be dealing with tens of thousands, perhaps not tens of thousands, but certainly thousands of base stations. And you had to do it in all countries. So the interest was, could we, UK, go off and do our own thing while we had initially high power transmitters from Band 1 because they were still active, and then subsequently land mobile. This is the Polish frequency allocation table. And the interest, therefore, was, could we do something with it? Could it be made into a mobile radio frequency band? Because Ofcom at that time were hell-bent on selling everything, any bit of spectrum that would work, they were interested in selling. And we'd at that point got Band 3 and the likes, all active PMR activities. So I got involved in commenting and doing a project in whether or not this band was we could do something with it. And I don't have anything from that era at all about what we did, but I did dig up Roger Fudge's PhD thesis. Roger Fudge around that time, and I think maybe later, and I think he was a mature student, he must have been, this was his PhD thesis, and it was about re-engineering VHF for all these opportunities that were coming along in the 80s. And it's interesting what he says. He says the distance for such communications, and we're talking here about, in that case, interference, because we're getting interference in from those distant stations. The distance for such communications is some 1,000 to 2,000 kilometers. Now, that's the first time we see that. And we're going to see that distance again and again, that 1,000 to 2,000 kilometer range. And of course, he's looking at it as an interferer, a Polish broadcast station or whatever. And thus the UK would be vulnerable to transmissions from southern Spain, northern Italy, Romania, etc. And of course, that's what we know as the 50 meg band. Doesn't mean, incidentally, we'll see this, that Sporadic E is not unique to 50 megs. It's in this region, it's in this lower VHF region that it seems to work. He went on to say, even if the interference knocks out the PMR service for 36 seconds every hour, he says it would be bad, because of course we'd have to employ frequency hopping techniques to avoid the interference. But if it occurred 15 minutes a day, that's terrible. And as he says there, 3.6, I don't know quite why he says 3.65. I think that's just 365 days. So 1%, 3.65 days a year, it'd be disastrous. And he then goes on to say time statistics are very worrying. The significant likelihood of communications being unusable. So that's the first time that we, shortly after that, of course, we got 50 megahertz. But at that point, Ofcom were terribly interested in selling this spectrum. And the interest was, what do we do with it? And of course, instantly, Sporadic E was a problem, because it allowed signals to propagate from distant places 1 to 2,000 kilometers away, and we'll modify that later on, but 1 to 2,000 kilometers away, allowed signals into the UK, and that knocked out our services. So that's where I first came in. And subsequently, then I had a little dabble when my son got a license. And again, I've kind of resurrected the interest about 18 months or so ago on moving to Scotland. So that's where I am. Now, what's up there? The big interest, of course, is why is this happening? Where does it happen? Yes, it's E, sporadic E. What is that all about? Well, the answer is the E region. The E region of the upper atmosphere, and we're looking specifically, and quite specifically, at a region or a layer at about 100 kilometers up. Up there is the interest to us, of course, is that we're not dealing with the troposphere. We're not dealing with where the weather is. We're not dealing with where aircraft fly. We're above that. We're up in the area where satellites are. We're up in where we can send rockets into and measure things. And of course, we're into this ionization, a region of ionization. And the important thing for us, and we'll see this as it goes on, is that there are meteors entering the atmosphere. And that's a critical point. So that's where we are. That's the focus of our interest tonight. And as I say, the interest there is, and we'll grow this a little bit, meteors. A little bit on geometry. We need to be quite precise about this, because it's important in telling what is and is not sporadic E propagation. The basic geometry is that station A will send a signal from an antenna at a launch angle, and if we're going to do anything with sporadic E, we've all learned that that launch angle should be quite shallow. Preferably zero, but it won't be zero because, well, variety of factors, but it's unlikely to be zero, but it might be, say, 10 degrees. And we're pushing a wavefront, and I've indicated it here, AABB. AABB is launching, it's diffusing as it goes, it spreads, it's not a pencil beam. We're inclined to draw things as pencil beams, but it isn't a pencil beam, it spreads. And it gets to the a region of the ionosphere that we're talking about here, and could be other layers, but or other regions, but it's the E layer that we're interested in. And it turns. Now, there's debate about whether it's refracting. I've shown it here refracting, or whether it reflects or whether it scatters. Personally, I would go for refracting. That makes total sense. The others don't, but that's a different issue. And so it refracts and it turns. And it turns and turns towards the Earth. And it then continues on its track, diffusing again, spreading out as it gets down to station B. It may arrive at station B by some form of multipath. That's another possibility. But we get something at B, which is the vector sum of all arrivals from station A, having transited through the ionosphere. So that's the basic thing, the basic geometry. And now we'll put some figures on that basic geometry later on, and put some distances. But we've already pinned some 1,000, 2,000 kilometers across that distance between station A and B, and we'll qualify that and add to it as we go. So what's happening here? What is the E region? What is it all about? Well, it's a region. There are three. We all learned that in our foundation courses. So we've got the F region. The ones that we're interested in are the ones that are positive towards us, the F and the E. And it's not that the E region is not there, other than when we have special things that allow us to say, hey, it's sporadic E. The E region is always there. It's just that its ionization level, as measured in electrons per unit volume of space, and in this case, I think it's cubic centimeters, I think, this graph, it's there, but it's not as intense. The ionization is not as dense as the F region. And of course, you know that the F region breaks in the daytime into F2 and F1. F2 is very interesting because it's higher, and therefore things go a bit further. But the E region is still there. And of course, what's happening is, and I've shown it by the white arrow, what's happening is that we're getting it increase its density. As a result of some mechanisms, it's increasing sporadically, it's increasing its density. And therefore we're moving along the x-axis and increasing the electron density. And we'll look at how that happens, and I'll build a little model on how that happens. So we're looking specifically at 100 kilometers up in the sky, if you like, and we're looking at a densification of the E region electron density. If you like, it then starts to behave as F2 on steroids. It moves up towards being a super refractor for a short time, and hence sporadic. So that's the mechanism, that's what's happening. So let's just have a look at perhaps deciding, well, okay, but how do you know that it's sporadic E? Because the thing we need to watch, if we're not careful, we go rushing off and saying, it's sporadic E, it's 50 megs, it's sporadic E, it's got to be. No, it doesn't have to be. The F2 layer, the region that we've just talked about there, sometimes the maximum usable frequency, the MUF, rises up into the VHF region, and it helps propagation. It carries VHF. So it's not all sporadic E just because it happens to be happening at 50 megs. The same is true of the tropospheric lift conditions. You get inverse beam bending, and by that I mean is the Earth bulges in the way, and tropospheric conditions can be such that the Earth bulge inverts. And so the two stations are effectively looking at one another, inverse beam bending. I'm not talking about ducting. Ducting's a different phenomenon, but tropospheric lift and inverse beam bending gives us hundreds, if not thousands of kilometers sporadically as well. So we have to be a little careful. We have to do some of these tests. And the key thing is going back to that geometry. It's not so clear with FT8 and data modes, and we'll come to that. But certainly with phone, SSB actually proving that 1,200 kilometer, the 1,200 kilometer limit, which is kind of what you get if you do the trigonometry. You will prove that for a reasonable launch angle, up to 100 kilometers, you will get something like 1,200 kilometers. And we'll look at that in another graph as well. So that's a pretty good giveaway. If we're getting somewhere around the 1,000 to 1,500 kilometers, it's quite a good giveaway that that's probably sporadic E. Not certain, but we can say, yeah, could well be. And maybe there are some other things that will point towards it as well. So we have to be a little careful. And one of the it's like those questions that people never ask. Are you sure it's sporadic E? Of course it is. Of course it is. Well, you don't know. You don't actually know. So you have to go through a little process of, okay, maybe it is. Look, where's the station coming from? Okay, what are the conditions? Yes, it probably is. So that's just a point there to note. Now, I wanted also to just throw something out there to you and say, well, is there any fundamental limit to the distance that our signals can go? And the answer is yes, there is. If we assume that it's free space loss from our station to the E layer and back down to the other station, then the free space loss equation applies, 32 plus 20 log f plus 20 log d. And if you flip that round, then d in kilometers is the number whose logarithm is, and then you can work it out. So it's the system value, in other words, the absolute maximum loss between the transmitter port and the receiver port. And it becomes system value minus 32 minus 20 log f. 50 megs 20 log f is 34. So system value minus 32 minus 34 all over 20. The answer there becomes, if you calculate it for SSB, you'll see the figures that I've just put together. The system value is 166 dB, and for FT8 it's 186. So FT8 is 20 dB bigger in system value, therefore it goes further. And I just did a quick calculation there on hope I've done it right, but the antilogs. So it comes out at a maximum of 100,000 kilometers for SSB and 1,000,000 kilometers for FT8. That's assuming free space loss. We'll see later on that you actually have losses along the way. You only have to have 2 hops of E, so you go up, down, and you've got loss when it hits the ground. If it's not a C path, you've got loss. Most of us have got loss in front of our stations. Therefore, it's very unusual to actually have a free space path loss. And if you consider that it's a logarithmic thing, it's dropping as 20 log, then you don't have to go far to actually lose that 100,000 kilometers coming down to 5,000 or 6,000 as a maximum limit. But it's just useful to look at that. The FT8, because it is a slow speed, because it's got coding in it, it goes a lot further. And we'll maybe say a little bit more about that later on. So again, qualifying and saying, what is it we're talking about? There's a lot of talk about auroral E and equatorial E, sporadic E. And just to kick those two out, the auroral E, obviously if plasma's coming in from the sun, splats down the top of the UK, around the Earth, the UK, splats down the top of the Earth, that creates ionization itself. It may not set up an aurora, a radio aurora, but it will cause ionization. And that in itself then gives us a relatively weak ionization, not as good as we're going to go on and talk about, but nonetheless there is some, and that's termed auroral E. And then equatorial E is more about the fact that the sun's beating down on the ionosphere, pointing at it, and therefore it creates an ionization in itself, and that also provides us some support. We're talking here about mid-latitude, and we'll see specifically. I put it on here: 23 degrees north to up to 66 degrees north, and that's the classification. That's the characterization of mid-latitude, and that's what we're going to go on and talk about. So, into the crux then. What is it that's happening? And here's a busy slide. They say don't make slides busy. Here's a nice busy slide. So let's just wind our way around this. I said to you that what's happening is that the E region is densifying. It's densifying. We'll see how it comes to densify. Give you a little clue there. It's all about meteors. But it's densifying. It's moving from its normal state into a denser state, and it is supporting, but only for short periods of time, and it might or might not, hence sporadic, and it is densified for a period of time. As a result, we have the refraction occurring in VHF instead of being confined to HF. It extends, it supports VHF propagation, and that's literally what we're talking about. But it happens, and there are two terms for this. I've used the term here, patches. Other people call them clouds. And patches, I like the term patch. It's like a little sort of thing that you splat onto the E region, and that's the thing, that's that bit at that point on the E region that supports the propagation at that point in time. And I've shown it here. The essence of it is that these patches are small. They're not as big as I'm showing there. They seem to reckon that the thicknesses are somewhere between 0.5 kilometre and 5 kilometres thick, and something like 10 to 1,000 square kilometres in area. Now, 1,000 square kilometres is 30 kilometres by 30 kilometres, and it's up in the sky. So we're not talking about huge areas. We are talking about small patches, just lots of them. You'll see where the area of interest that I'm describing here is the Tropic of Cancer, 23 north, up to the Arctic at 66 degrees north. Now that gives us, and we've seen this in Roger Fudge's thing, and I've speculated there at this 1,200 kilometres. But remember that the signals are diffused, things are diffused as they go up. So you're seeing that the first thing is the one hop, in other words, up, down, range as taking us out to, and I've done it from the middle of the UK, so it's taking us out down to the Mediterranean. And two hop range is taking us, and you see there, taking us further out, out to the sort of 2,500 kilometres, that sort of range, and a bit more out to the far end of the Med. The important thing is that it is these patches have to exist at the point of refraction. We're not interested in what's going on above you, at your station there and then. We're interested in what's going on in the ionosphere and this densification process that's happening, and it's happening at a distance of, in this case, 600 kilometres or so away from you. We'll again, I'll say we'll modify that distance, but it's out at that sort of range. So what's happening is that you're getting patches occurring, let's say, over the western side of Germany on that bright green patch. And that's the thing that's giving us the propagation. It's what's happening out there in the ionosphere that matters. The patches, quite naturally, and we'll come to the model, reduce in intensity and size with latitude. So as we go further north, they get smaller. And just to cap that off and say, is this real? I've put it here as a fanciful thing. My patches are huge. They're not the size that I'm putting up there. Just look at that little thing that says summer 2007, and you're seeing there a projection of those patches. And the red, I think if I remember rightly, is something like 40% probability, and it's in the summer, and it's a very high. I think 2007 would be, the red area is about 40% chance of a sporadic E opening, and you can see, if you just look carefully, you can see the patches that we would be interested in occurring perhaps over northern Spain, Germany, and the likes. Not many up as far as Denmark and the likes. And so you see the nature, this idea that these patches reduce in intensity, going from red down to blue. Blue is a very small probability, and size and intensity with latitude. So that's a kind of projection of what's happening with all of the patches. And of course, what this is like a sort of time delayed thing where we're seeing all of those patches over a time period. But what's happening is the patches are, if you like, lighting up, dwindling, lighting up, dwindling, etc. as we go on. So, so let's just take a look at what's happening. Why does this happen? Why does this affect, and why are these patches created in the first place? I said it was all about meteors, and here's the kind of timeline, if you like. We're going to start with meteors. Now, we're not talking about meteors as in meteor showers. We're talking about the continuous bombarding of micrometeors, things about the size of a grain of sand and maybe slightly bigger, continuously across throughout the year, not just when there happens to be a shower. I've actually put for reference, the magic figure seems to me to be about 8,000 meteors a day. And I've put a little graph down here. This one's stolen from David Bacon's, one of his papers, where it shows about 8,000 on average, peaking to something like 11,000 during the summer and dwindling away to 5,000 or 6,000 in the winter. And instantly, of course, that tells you, if it's about meteors, then it's all about the summer. The intensity of the meteors occurs over the summer. Therefore, we're more likely to get these patches created in the summer months. But what happens is these meteors come into the Earth's atmosphere. They ablate, in other words, the atoms get stripped off the lump. And of course, in the first place, anyway, the sun is there cooking. So if the sun isn't there, it's not going to happen. We'll qualify that a little bit. But the sun cooks the atoms. The ions are produced. So most of this is about metal ions and metal atoms. So we're looking at about iron and the likes, iron and calcium, for example. Not calcium, I was going to say potassium. And so the sun is cooking the atoms, and we're getting a plasma created. Now, the plasma stabilizes, because naturally what should happen is if you create a positive charge and a negative charge and you leave them together, they'll just recombine and end up with no charge. So you end up with a plasma which stabilizes, which has neutral atoms in between that actually keeps them all in a stable position. So there is some plasma created, and then that plasma descends. And this is the important bit. It descends down through the ionosphere, and it gets to the E region. And at that point, the conditions are favourable. We'll go through that in a bit. The conditions are favourable as a result of winds and tides up in that upper atmosphere. The plasma is densified. It doesn't stop, it's still continuing down, so it's only there for a short period of time, hence the patches, hence sporadic, and it descends below the E and disperses. It just becomes part of the normal Earth's atmosphere, and that's the end of it. It recombines, and we end up with a little bit of metal atoms up in the atmosphere. So that's the important thing. We start with the meteors end up with atoms stripped off, ions are produced, we get a plasma, the plasma descends, winds and tides densify the plasma. That's us, we're on. If that's happened in the right way and the density is right for us, then we're on, we've got a lift, and then it fizzles. So that's the actual process. In terms of time and when it actually occurs, the important thing there is that the node, or the densified node, a node just being a sort of point, a concentration of the densified plasma, descends. And here's how there are three different mechanisms. Probably the most familiar one to us, and the one that we should really focus on perhaps, is the orange one. And what's happening is here it comes in on the left, 140 kilometers up in the sky, down it comes. Remember that the E region is nearly there. It's kind of interesting, but it's not supporting VHF until the arrival of this extra density cloud, which combines with what's already there to give us the patch that's capable of supporting the refraction. And we see when this happens, This occurs typically, and remember, it's all about, everything coalescing, everything coming together. That includes a good bit of sun's cooking. And we get, at the refraction point, we get anything from 1500 hours local out to 1900 hours local, being quite intense. And before that, you get a little bit less. And after that, you get a little bit less. And if you think about that, of course, if we're looking out to the east, then we're 1 to 2 hours behind this. So 1 to 2 hours behind the 1500 hours for the start would be a start time of about 1 o'clock in the afternoon, UTC, if we're that we'd be looking at that sporadic E lift. So that's how that happens, and then of course it carries on descending and fizzles out. We've got two others. We've got one that's comes in in the early morning. That gives us a week densification, and one in the evening, which is quite a rapid descent. And they're not benefiting from the same sun's cooking, but they are still there, and we get an opening in the small hours. So that's kind of what we're talking about. Now, the important thing is that we can detect this. Radar, LiDAR can detect this. And there's a model around. I was reading one paper of a thing called Gaia. There is a model of the upper atmosphere, and people are very interested in this because of navigation satellites and other things that we would wish to communicate with professionally that transit the ionosphere. So there is some significant interest in this. It's just that it's not the interest we have particularly. There are plenty of people modeling it from the viewpoint of understanding how it works. We want to model it perhaps as to, for example, shall I go out for the day and go walk a mountain, or shall I stay in and work some sporadic E? Do I feel lucky? Well, if we could actually predict it, then maybe we'd be able to make a better judgment. But there we are. So that's what's happening. I'm going to just then run through quickly a model of the sporadic E. Now, this is a very classic and quite simple modeling method I'm going to use. It's called an input process output model. It's basically input is consumed by the process to produce the output. There are things called enablers. There are things that, funnily enough, enable the process. They don't actually get consumed by the process. And there are constraints. And it's a very common way of modeling things, a basic kind of way. And what I thought I'd do is try and see if we can actually model sporadic E. So let's have a go at explaining. The input is some kind of homogeneous, inadequate density of plasma. So there is some plasma coming in. It isn't at the right density to support the VHF propagation that we're talking about. And that's the input. The output is a localized patches, a localized adequate density plasma. So, and that gives us then the chance of a sporadic E opening. That's the simple process. So what enables it? Well, one thing that's also an input is the meteor characteristics. Clearly, the more active the meteor, the higher energy the meteor, the higher velocity the meteor, the more likelihood that this is actually going to happen. So we've got the meteor characteristics being consumed by the system as well. But we then got a whole bunch of things that might impinge upon this process and might enable it or might actually constrain it. Now, I may have got the enablers and the constraints. There's a little bit of a debate as to which is which and whether some of them actually are. For example, the atmospheric gravity waves, but I'll run through them. First of all, the Earth's rotating. That's an enabler. Otherwise, we wouldn't be sweeping up the meteors. The sun's beating down. Otherwise, we wouldn't have a basic E region that was kind of there or thereabouts. So we do need the sun. I'll skip to, no, we'll run across. Wind shear is where you have in the upper atmosphere winds. In other words, movements of particles, not kind of winds that we're talking about on the surface of the Earth, but movements of particles in winds. And if we have one wind going one way and one wind going the other, then we will create this node in the middle of stagnant plasma. And if we do that, if we've got these shears, the more shears we've got, in principle, the more nodes we've got, and the more nodes we've got, the more likelihood a patch will be produced. I'm going to jump just to winds and tides. The same kind of thing. There are winds, I've mentioned, obviously, because there are winds and wind shear, and tides that are tidal movements that ebb and flow in the upper atmosphere, and they can have an effect, because what we're trying to do is set up and sustain a node. The Earth's magnetic field has a bearing, because that's helping hold the plasma, the charged particles, in one place, so that helps us. The magnetic field disturbance, and some people say, well, it's going to be great tomorrow because KP, the magnetic disturbance index, is going to be low tomorrow, therefore we're going to get sporadic E. No, it may be low tomorrow, which indicates that there's low magnetic field disturbance, but that doesn't mean that the rest of the stuff coalesces and is all in the right lines. But what it does mean, the converse is true. If you have a disturbed magnetic field, then creating a stable high-density node that will support propagation is less likely, because the magnetic field is disturbed and is therefore trying to pull those particles all over. So that's an act against us. It's not an enabler. If KP rises, then we're likely to get less likely to get a sporadic E opening. That then brings us to latitude. Fine, we said that the availability of patches and the density of patches drops as you go further north. And of course, time we've talked about, because there is this mechanism where the plasma drops, the nodes drop. Once formed, they drop, and they hit the E region at the right time. That leaves us then with an area where people say, yes, well, it's all about jet streams. It's all about the atmospheric jet stream, the high altitude direct jet stream. No, it's all about mountains. The difficulty is that all of these effects are the tropospheric effects, or the weather effects, are happening way, way below. But what happens is that it may well be that turbulence from a mountain will create an atmospheric gravity wave, and I skipped that one over neatly, would create a gravity wave which would propagate upwards and may destroy the node and may cause a problem to the node. And the same is true of thunderstorms. Massive thunderstorms over Italy may well propagate upwards through atmospheric gravity waves to cause us less dense E region plasma. So you can see the beginnings of a model. Have people got it? Have we got a proper model? Can we actually run it? No, we can't. We can explain it, we can see it, measure it, look at it happening, but we can't yet predict. So let's just look towards the end. Actually overrunning a little bit, but hopefully you'll bear with me. I'll be done in about 7 or 8 minutes. This is what we can say. A 50 meg path will exist. Here's a typical way that we can describe what's going on. A 50 meg path will exist at midday between UK and Italy for 20% of days across the summer, or however else we want to qualify. Or there's a 1% chance that there's going to be a 15-minute opening at 144, about 2 meters, over a 2,000 kilometre path from UK down to the Med. We can say that's sort of probability because that's experiential. We know that that's what happens. There's plenty of people measured it, and we can say that. What we can't do is say, will it be good tomorrow? And we've all played that game. Brilliant today, gonna have a go tomorrow. Oh, rubbish tomorrow, no opening. Here's, I think, a summary of the 20% of days range that you would typically get. I'm measuring range here not by FT8 or SSB, I'm measuring it in field strength in microvolts per meter. But it's a picture I want you to see, not something that's absolute. The point is that a fairly modest setup at, in this case, 50 megahertz, a fairly modest setup will get you able to play with SSB across the range of about 1,000 kilometers, that big blob A, that will get you up to maybe 2,000 kilometers with SSB in a fairly modest setup. And that will extend, there's another re-entry there of around the 4,000 kilometer range. At 2 meters, it occurs less frequently, and therefore we're seeing, and it's centered around 2,000 kilometers. And if you want to look out towards the 4,000 to 5,000 kilometers, then you're looking at having a superior setup, either going to FT8, CW, or having a very good equipment setup. And that was just an interesting graph I thought came from, you see there, G0 MJW, Mike Wilkins, I think it is. That gives you, that really characterizes the sorts of distances that we're talking about here. Experience then that I've had, and I haven't got a great experience, I have to admit, so therefore I'm quite happy to open to others who might have. But here's a day in June 2022. What happened was that Europe lit up, and you can see actually it was more like the image down on, this is using PSK Reporter, and I'm using FT8 here, and you can see down in the right hand image, I'm lighting up stations all over Europe. Now, that was happening at 12:05 UTC. That was also happening, started to happen a bit after 12:05, because otherwise you'd see it there. So it started, and I worked a lot of SSB into Europe. And I then thought, look, this is so intense. This is really going places. This is so intense. In principle, we ought to see things happen more out towards the US as the day goes on. So I then turned the beam northwest, and at about 15:35, this is the picture I was getting, I was starting to light up. A little bit earlier than that, you'll see 17 minutes earlier. We're looking at Newfoundland and the likes, and then out ultimately to a single. I only made one QSO because, of course, just because you light somebody up doesn't mean there's an operator there to actually press the button and fire back at you. But I got somebody in Ohio respond, and that's about 5,800 kilometers. And no sooner had I done it, but it started to track back. The PSK Reporter started to diminish, and you see it there in the right-hand side where it's saying 4 hours, then back out to 5 hours, and it literally, the lift, the improved conditions started. I started to light stations up in eastern Canada and down into eastern US, and then I stopped, worked a station, and then it all diminished, and effectively, as soon as it had happened, it was over. And I reckon that particular path, those paths were open to me for probably about 30 minutes. I think it lasted about 30 minutes that I was sitting there. It didn't mean that I worked more than one station, but 30 minutes. So that shows you this sort of sporadic nature. It might have been there, it was there. Things were quite intense in Europe, supporting lots of SSB. So therefore, SSB being 20 dB worse off, if you like, than FT8. If it'll work I actually proved that it was working very strongly for FT8, so I switched to SSB, worked SSB. I wonder what's happening in the US, turned the beam, and that's what happened. In terms of actually trying to think, when will this happen? It's all about chance. It's all about the probability. And in the case of something as long distance as that, you're looking at 2 hops. So you're looking at the transmitter going up to the first patch, reflecting off the C, back up to the second patch, refracting on that, and back down to the receiver. And what you've got then is the probability of a workable path, is the probability that there's actually going to be the first hop works, and the second hop works, and you're going to multiply them. So therefore, there's a 10% chance of one times 10% chance of the other. You've got a 1% chance of the whole hop working. So we're really saying that whether this works or not, is all about the probability of patch 1 being there in the right density at the right time, at the right location, and patch 2 likewise being there to support. If one of them isn't there, it doesn't happen. If both of them are there, then it does. But you've a much lower probability simply because you're using the propagation is by 2 hops. And don't forget, of course, we're saying here that I'm drawing it like it's a ray. It's not. It's diffused energy. But I'm going to that just at this point. Typically, the reflection loss is 0 dB for C. So in other words, it's a perfect reflection off the sea. It's not a perfect reflection off the land. And therefore, of course, sea paths are nice because they don't lose energy, whereas land paths lose energy. And I'm assuming here that refraction loss through the patches is 0. There's no loss. I'm not actually sure if that's true, but I think it probably is, because there's no reason to expect it to be too high. But whether it's actually 0 or not, I'm not sure. So basically, in terms of probability, it's a low probability thing. This is FT8, and this was a couple of graphs from the day. The important thing, I think, the center orange oblong, is that you see the thing being established, the decode being established at the top, but then you see it fading out. And that's very classic. Anybody that's worked sporadic E, you see it come, it goes. You think you can get somebody, you call and call and call, they don't reply, they've gone, and that's the end of it. Again, classically sporadic. And here then, just coming to the close, this is a waterfall from GEM4OS, and it shows you one of the openings around in 50 megs. It shows you the CW end being quite populated. It shows you the phone signals being quite high, that was I don't know which date that was. It was this year. I don't know whether it was the same day as I was working, but that shows you the signal intensity in the middle of a lift. And of course, the answer would be when the lift was not there, when the sporadic E was not there, that trace would be flat and there would be nothing. So likewise, the FT8, the GM0 SCA and EI7GL, these plots, one is from DX Maps, I think they're both from DX Maps actually, but it shows you the way you can infer where the patch might be. In the case of the upper one, you can see that it's somewhere over southern Germany. The sort of the locus of points, the intersections of all the paths, and the same with the EI7GL one. You can see that it's somewhere, that the patch there is somewhere north of Denmark in that particular case, and that's so. What can we say about it? Well, the first thing is we can play in it, that's sure. There's plenty of stuff been written from radiometers and you can play in it. The second thing is you can detect it, and the professionals detect it. You can sense it, in the case of, you can sense it using vertical incidence sounders. You can describe it statistically, so chance of a 15-minute opening. You can model it in a general term, but you can't predict it because there are too many variables, and the variables have to align, and the probability of that is quite low. So that is a quick gallop across sporadic E propagation.